Okay, so the firewall paradox. You may have noticed in some of this story, notions from quantum information theory started to creep in, or at least personalities from quantum information theory started to creep in, like Preskel and Hayden in this analysis of the black hole thought experiment. It turned out that you had to know quite a bit of quantum information theory, of quantum computing, in order to come up with this example of that Preskel and Hayden came up, the much better strategy for trying to verify Xeroxing, which still failed but got as close as you're allowed to get. And this theorem that I quoted from Page about how much information you can learn about the quantum state of a system by accessing only a subsystem. How much information can you learn about the quantum state of the black hole plus radiation if you see only the radiation, if you can put your fingers only on the radiation? Those are quantum information theory results, and it turns out that that's probably really at the heart of the problems that we face with black holes, unitarity, and the equivalence principle. And so in order to, that's hitting us again with the firewall paradox. And so I'm saying that in order to justify why I'm going to start with a few slides that basically state fairly elementary or at least well-known results from quantum mechanics. And then it turns out that you just need to put a few of these things together and you have your contradiction. So bear with me. So here is what you would call a bipartite system. Some Hilbert space that's the product space of system A and B. Each of them have a Hilbert space, HA and HB. My notation is going to be that n sub A is the log of the dimension of the Hilbert space A, something that closely related to, say, the number of binary degrees of freedom or qubits. N sub A, I guess, divided by log 2 would be the number of qubits. Now, if I have my full system, AB, in some arbitrary state described by the density matrix rho AB, this could be pure, it could be mixed, it's well known that if I have access to system A only and not to B, then I can describe all the experiments that I can possibly do in terms of a density matrix for A alone, which I can obtain from rho AB by tracing, by what's called a partial trace over the Hilbert space HB. And by a partial trace means that I pick any basis for the Hilbert space HB, and I do this sum. So little b is a complete basis for the Hilbert space B. Which basis I pick doesn't play any role in the final answer. Okay, so that's what's called a partial trace. It allows you to extract the density matrix for a subsystem, which is completely sufficient to describe all the experiments that I can possibly do on this subsystem. Okay, from the density matrix for the full system. If I have a density matrix rho A, I can define a von Neumann entropy of it like so, minus trace rho log rho. Okay, so for example, if rho A is actually a pure state, then this entropy will be 0. If it's a maximally mixed state, it could be with equal probability in any one of the states of its Hilbert space, then this density matrix will be proportional to the unit matrix. It'll be, well, e to the minus NA times the unit matrix. Every state has the same probability. I have no information at all in that case. Okay. And it can be anything in between. And that, if I have no information at all, then SA is equal to NA. Right, this is this statement. If I'm in a pure state, I have a lot of information. If I'm in a mixed state, I have none. Excuse me. Okay. So what's going to be important for us is the notion of maximal entanglement. We're going to say that A is maximally entangled with B if and only if the von Neumann entropy of the reduced density matrix for A is equal to the size of the Hilbert space, the log of the dimension of the Hilbert space of A. Basically, if I have no information at all about what state A is in without having access to B, then A is maximally entangled with B. Okay. This is equivalent, as I said, to the density matrix being proportional to the unit matrix. This is supposed to be an I denoting a unit matrix. And you can only have maximal entanglement if the system B is larger than A or equally large. Otherwise, there's not enough in B that you can entangle A with. Okay, so what's an example of this? Well, let's take 2 qubits. Okay, so system A is something that's spanned by a Hilbert space with bases 0 and 1, and system B, the Hilbert space, is also spanned by some 0 and 1. And I can consider this EPR state 0, 0 plus 1, 1 over square root of 2. That's maximally entangled. Okay, if I have access only to the first subsystem corresponding to the first number in each of these states, that subsystem is in a completely mixed density matrix. Rho A equals a half. And by the way, this is of course true for any other Bell states. So Bell states are these things here. They're maximally entangled states. In fact, such states form a complete basis. That's a good thing to keep in mind in the context of the firewall paradox, because it makes it very difficult to try to resolve the paradox by ascribing somehow different dynamics to entangled states versus product states. Because by linearity, they have to have the same dynamics. I can build a product state out of entangled states. I can build entangled states out of product states by linearity. So you can't distinguish between them dynamically. They form a complete basis if the two systems are of equal size. Otherwise, I need some extra basis elements for B. Okay, so this is just the definition of what I'm going to mean by maximally entangled, just because it plays such an important role in the argument that I wanted to be very explicit about it. The second concept that we're going to need to know, which maybe isn't as well known, but it's actually, I think, intuitively also not too hard to understand, is the monogamy of the entanglement. So in order to discuss that, I actually need a tripartite system. I need systems A and B and C. And just to give you a crude example to start with here, let's say that A and B are maximally entangled. They're in this EPR state. Okay, they're in this state. Okay, and my question is, can I find any state, mixed or pure, for the whole system A, B, C, such that, well, A and B are in this state if I look at them just by themselves. But B is also entangled with C. B is entangled maximally with A, but also entangled with C. And the answer is no. In fact, if A is maximally entangled with B, then B cannot be at all entangled or even correlated with C. And this follows from a theorem that you can prove called the strong subadditivity of the entanglement entropy, which is this inequality. Okay, and you can see this. If I wanted AB to be in this state, then the von Neumann entropy of AB is 0, because AB is in a pure state. If I also want BC to be in that state, then the von Neumann entropy of BC is 0, so the right-hand side is 0. But just look at SB, which I can compute from this state by tracing over A. SB is going to be log 2. So I have a manifest contradiction. And again, more generally, this tells us that I can make B somewhat entangled with A and also somewhat entangled with C, but I'm going to have to trade. I can't have too much entanglement, combined entanglement. And this inequality tells me what kind of trading is allowed. But certainly if I have maximal entanglement of B with something, then it must be completely unentangled and uncorrelated with everything else. And that's the key message. Okay. Oh, by the way, before I go on, just to give you an intuitive feel for why this had to be true, again, think of the EPR experiment. I have, you know, system A and B are, you know, spin up plus spin down, spin down. Now I separate them from each other, and I measure A, and I find spin up. I measure it in the Z basis, let's say. I find spin up in the Z basis. Now I know that B is going to have to show me spin up in the Z basis if I go there and measure that. In fact, I can do that in a space-like related way. Doesn't matter. In the end, when I bring everybody back together, I know that I had to get the same direction of the spin for A and B. Now suppose that there was a spin C, which was also in an EPR state with B. And I brought that far away, and I measure C in the X basis, and I get spin up in the X basis. Now by the same logic, when everybody gets back together at the end, I have to find spin B being in spin up in the X basis. So now I have a contradiction. What's the poor B guy going to do? It can't make both of them happy. Right, so that's why you can't have maximal entanglement with more than one system. Yeah?
There's something like the Green-Horn-Thallinger state, right, which has maximal entanglement, as far as I know, between the Bipartite System, between the three states. So is it so that then you have, so to say, the maximum what you can get on the DC system and also the maximum entanglement what you can get on the AB system if you look at this particular state?
Yeah, I'm sure he didn't violate this inequality. So it must be, I'm afraid I'm not, you know, I can't, we'd have to sit down, stare at the state and figure out what's going on. Right, so there's probably some trade-off going on where right. Yeah.
I thought that the notion of bipartite entanglement of qubits, given by the Cayley entanglement, there is a notion.
It's not that you can't have, right, no, sorry. It's not, nobody's claiming that you can't have entanglement between more than two subsystems. But it's limited by this inequality. That's all. And in this inequality, of course, you can permute A, B, and C, so you can apply it to various pairs. So I defined it. I defined it. I defined it. What I call maximal entanglement is this. SA equals NA. And it's defined, I'm sorry, it's defined only if A and B are together in a pure state. It's going to be the only case of concern to me. That probably precludes application of my definition of maximal entanglement to any situation where there's non-trivial entanglement between three systems, because then no two of them are going to be in a pure state. But that's the definition that's going to be useful for me. So just the definition that I am giving for maximal entanglement is only valid. Sorry, yes?
You have three different qubits.
Yeah.
You can make, I mean, the interface is larger.
Yeah. And in particular, it may not be true that any two of them are in a pure state.
In that sense.
And so my definition cannot even be, I mean, then by that definition, it's impossible for any of them to be maximally entangled with any other. Right? Because the very starting point of the assumption that underlies the definition would not be satisfied in a generic state for a tripartite system. Again, that's, you know, there may be other things you can define. This is the definition that's going to be useful in this context, and if you don't like the word maximal entanglement in this context, then, you know, substitute your other favorite word for it, but there's a mathematical statement that it corresponds to, which is the useful one. Okay, where were we? Good. So this is quantum information theory. One more thing about quantum information theory is the Page theorem. This we do not actually need for the firewall argument. Okay, it can be eliminated. However, it greatly simplifies the presentation, and since it doesn't, in the end, you know, help that much to assume that the Page theorem is somehow not applicable for black holes, it doesn't help to question that. So then we might as well go with a natural assumption that simplifies the presentation, and I'm going to do that. I hope that's all right. So this is the theorem I mentioned earlier. about the typical entropy of a subsystem, or the average entropy of a subsystem. And you don't need to think about black holes. Just think about a system consisting of a large number of qubits, and so on. And let me put that system into a typical quantum state. And by typical, I mean Haar random. Okay, so in particular, it's not going to be this state. This state is extremely atypical. It's a product state. Right? I could take this bit out, and it would just be in a pure state all by itself. A typical state is not at all like that. In a typical state, if I take this bit out, it's going to be in a completely mixed state. I have no, I get no information about the system by looking at just one bit. And what Page showed is that if I am in a typical quantum state, I have to look at least half of the qubits in order to get even one bit of information out. And then if I start looking at more and more, I get nearly all the information out. Okay, so that is this statement. Of course, it doesn't have to be a bunch of spins. Just take any bipartite system. You have a smaller subsystem and a larger subsystem, and you assume that together they're in a random pure state, or really what he does is average with a Haar measure over all pure states. So the Haar measure is just some natural measure on the Hilbert space that you can look up. That's the thing you want to do. And the statement is that in that case, that the smaller subsystem will be nearly maximally entangled with the larger one. Notice the correct, so without this term here, it will be exactly maximal entanglement. If NA is equal to NB, so if I'm looking at exactly half of the system, then I depart from maximal entanglement by an entropy difference of 1/2. So even if I look at half the system, I don't even get one bit of information yet. One bit would be log 2. Okay, so this is a little bit less than 1 bit of information that I've learned. And if I look at less than half of the subsystem, less than half of the full system, then you see it's a half times some exponentially small suppression in the difference between, so if NA minus NB is whatever, 100, so there are 200 bits, I'm looking at 50 of them. Well, then I have gained 1/2 times e to the minus 100 bits of information. Nothing. Completely negligible. Intuitively, what's happening is that the larger subsystem is acting like a thermal bath to a good approximation on the smaller subsystem. It's true that overall they're in a pure state, but I'm looking at something that's so small compared to something else that's so big that the small thing is basically in a thermal bath. Okay, this is all there is as far as just pure quantum mechanics is concerned. Now we're going to do some quantum field theory. Any questions? I should watch the time. Okay. Okay, so if there are no questions, we need to add one more ingredient before we can put it all together. This unroot state that I've alluded to a few times, it's basically a dumbed-down version of what Hawking did. Right? Hawking said, well, at late times, the quantum field, at late times, I can think of it as sitting on a Cauchy surface that looks like this. It consists of a region near infinity, large radius, and all the stuff that falls into the black hole. And I get separate sets of modes for these two pieces. And then if I start with a pure state down here, but at late times I have access only to, in some sense, half of the final Cauchy surface, or at least one part of it and not the whole thing, then I find that this part of it is in a thermal state. Now, this was done on this background of the black hole, the full geometry, he did the thing. But it turns out that the key features of what's happening here can actually be understood by zooming in on some region near the horizon of the black hole. And as I said, near the horizon, the space-time, to a good approximation, can be described as Minkowski space if I don't look at distances that are comparable to the Schwarzschild radius. If I look at short distances, then that should work. I'm sorry, there's some sort of resonance as soon as it bounces with the blackboard. And so what you can do as a sort of alternative to deriving Hawking radiation is you can consider flat space, so just consider Minkowski space, which lives here near the horizon. And in Minkowski space, what we can do is we can define these two lines here. X is plus minus t. Okay, and if we have more dimensions, they just go along for the ride, so we're not doing anything to y and z. And we can consider accelerated observers which have access to only one of these two what are called Rindler wedges. So this thing here would be called the left Rindler wedge. It's the part of the spacetime that can be probed by an observer with fixed acceleration where the acceleration is related to the closest approach to the origin. And similarly, there's a family of accelerated observers. The ones out here don't accelerate so much, but they also stay farther from the origin. That acts as the right Rindler wedge. Okay, you can analyze Minkowski space from the point of view of these two Rindler wedges. It's just a very perhaps awkward-seeming way of analyzing the spacetime. You're just breaking it into two pieces. In the left Rindler wedge, this would be a Cauchy surface for the left Rindler wedge. And that green thing here, that's supposed to be green, is a Cauchy surface for the right Rindler wedge. You can find a complete set of modes for, say, a scalar field with support only in the right wedge. You can find a complete set of modes with support only in the left wedge. Okay. You can build a Fock space just for the right wedge. You can build a Fock space just for the left wedge by quantizing with respect to the creation and annihilation operators defined from these modes. And that should be good enough. Just like these modes, when you put them together, are sufficient. You can find linear combinations as long as you use both the left and the right wedge. You can make up any quantum field in Minkowski space from them. You can also make any quantum state that will be defined in the usual way in Minkowski space with respect to the modes that have support all across the spacetime in terms of sums over products of states in the left and right Fock space for the Rindler wedges. Okay, and in particular, you can write the Minkowski vacuum that way. Right? That's just some quantum state. It's very easy to define it in terms of, well, it's annihilated by all the standard annihilation operators that are defined with respect to the usual modes. But I can write it in terms of these left and right Rindler modes. So J is supposed to represent something like, well, it's a discrete version of basically the frequency. This is the frequency associated with J. And this is an occupation number. So I've got, this is, so mode by mode, this is a very entangled state. The Minkowski vacuum is a very entangled state, something like the EPR state. So 0 right, 0 left, plus, well, it's not 1, so occupation number 0. Now, occupation number 1 has an e to the minus pi omega in front of it. And so on, but they're very entangled. Okay, and what you find is that if you trace over one side, if you have access only to the right Rindler wedge, but not to the left one, such as these accelerated observers do, or such as somebody who lives at large radius in a black hole does, what you want to identify, by the way, is the black hole horizon with this Rindler horizon. Okay, close to the black hole horizon, I'm hovering at fixed radius. That's exactly like a Rindler observer in flat space. In fact, that's exactly what it looks like to me. It looks like flat space on distances shorter than the Schwarzschild radius. If I'm hovering like 1/1000th of a Schwarzschild radius away from the horizon, then this is a very good description. And what I don't have access to, since I'm hovering at fixed radius, is the inside of the black hole. So I get to trace over this left Rindler wedge. And what you find is a thermal state. And really, the thermal radiation that Hawking finds is just the redshifting of that thermal state out to infinity. The thermal particles that you would detect with a detector near the horizon if you're hovering, well, some of them make it out to infinity. The ones with high angular momentum actually fall back into the black hole usually, so they have a higher barrier to get out. And so there's a difference actually. It's not completely true that the radiation is thermal in the sense that it's thermal near the horizon, but there are suppression factors that depend on the angular momentum for which particles actually get out to infinity, and it's mostly the S wave that gets out. But you can put that in when you interpolate between what a Rindler observer sees here and what an observer sees at large distances. So this is really the same calculation. This is the essence of what Hawking calculated. I should have set this to not sleep. Okay. And when I said that Hawking showed that his radiation state is really a thermal state, this is really what he was doing. He was tracing over the inside of the black hole. Okay. So,
sorry, can I ask a question about this
yes.
state? This is not the most general linear combination. What is the meaning of this exponential prefactor?
That's what makes it thermal. So it's not a completely, right. It's a very specific state. It's a very specific state, and let me see if I wrote it down. No, okay. It's a very specific state, but it's this factor that makes it look like a thermal state. In other words, that suppresses each energy level by precisely the right Boltzmann suppression when I trace over the left wedge. Of course, it doesn't matter which left or right is all symmetric, but when I trace over one of them, right? You can, well, what you see is that the temperature is essentially given by the acceleration wherever you are. You see a local temperature that's given by the acceleration. That's the Unruh effect.
So omega j is like the energy.
I'm sorry?
Omega j is like the energy of the chase level. What is omega j?
Omega j is the Rindler frequency. So that's related to the energy as would be measured according to the Killing vector field. There's a time-like Killing vector field which has these orbits, these accelerated observers orbits, that lives in the Rindler wedge. And you can define an energy with respect to that time-like Killing vector field, and these frequencies actually correspond to the energy of particles as measured by such observers. And that time-like Killing vector field that you would locally define in Rindler space near the horizon precisely agrees with the time-like Killing vector field that we have in the Schwarzschild metric, right? That has orbits which are constant r, constant radius. So that's why you can really use this argument to interpolate to Hawking radiation. Good. So this is the key takeaway message is there is in the Minkowski vacuum. If you want to have the Minkowski vacuum or anything closely approximating it near the horizon, you're going to have a lot of entanglement between the inside and the outside of the black hole. Let me redraw this messy black hole. It's not maximal entanglement really, but it's a lot of entanglement. So think of putting your Rindler space locally here. This is supposed to be some region much less than RS, but much greater than the Planck scale, say. And by making the black hole large, I can make such regions arbitrarily large. I should have Minkowski space in such a region. So what you should think of is an observer. Why did I put this Rindler wedge precisely here? Well, I'm going to put it wherever Alice falls into the black hole. right? And Alice should see flat space here near the horizon. And it's useful to write flat space in this Rindler decomposition for our purposes, because it tells us that some Hawking particle that's going out here must be entangled with some mode in here. Looks like a happy person now. This is a happy person because there's no firewall at the horizon. That's how you have no firewall. Okay. All right, so now we're ready for the amps argument. It's going to be very simple because we did all our homework already. We're going to make a black hole, big black hole. We're going to let it half evaporate. Or more than half, but at least half. Why at least half? Because I want to use the Page theorem. I want to be in a situation where what remains of the black hole is maximally entangled, in the sense of my definition, with the Hawking radiation that already went out. Right? I have access to more than half of the whole system. The remaining black hole is less than half of the whole system. That's the situation I want to be in, and I'm certainly allowed to consider that. Okay, what I'm really using, of course, is unitarity when I say that, because it was important in the Page theorem that the whole system is in a pure state. In fact, I'm actually assuming that it's in a typical pure state to some extent. So I'm assuming that the black hole dynamics is somewhat scrambling, so that no matter how I make the black hole, in the end, if I grab, half of the system, the Page theorem actually applies. Okay. Again, it turns out that it doesn't seem like questioning that is going to help very much, which is why I'm not doing it here in order to present the argument relatively smoothly. But it's certainly worth going through. Well, could it be that the black hole is not in a typical pure state, and so on? You need to question all these things. I think it doesn't help. Okay, so there's two ways of thinking about this. Either I can think of it as, well, there's still some black hole left, and it is it has some quantum state which I don't really have access to, which is maximally entangled with the early Hawking radiation. Early Hawking radiation means whatever already went out prior to when Alice fell into the black hole. So there's some early Hawking radiation that already went out, which I think here I'm calling A. And then there's some late Hawking radiation. So I can instead of thinking of the black hole as the thing that's maximally entangled with the early Hawking radiation, I could also think of whatever the black hole has yet to emit. I don't know, A prime. By the time it completely evaporates, and say that's the thing that's maximally entangled with the early Hawking radiation. It doesn't matter. The two things are basically the same. They're just related by time evolution. Okay. But it's really, when I'm applying the unitarity of the S matrix, it's the system AA prime that must be pure, because the S matrix applies at infinity. It tells me what gets out to infinity. And what I'm now going to do is use another one of the assumptions of black hole complementarity, which is that I get to use effective field theory outside the horizon. And so all these Hawking particles that arrive at infinity, I get to ask, well, where were they coming from? Well, they came from somewhere here. They came from near the horizon. If you follow them back, what actually happens, if you follow a wave packet back, is that it starts sort of hugging the horizon. It gets very blue shifted, very short wavelength. And basically, its wavelength is always comparable to its distance from the horizon. Once it enters the near horizon zone, which, remember, is some r equals, I don't know, 3m, some order 1 factor larger than the horizon. Okay, then it has this sort of universal behavior where it starts really hugging the horizon. So if I say that A prime, the late Hawking radiation being the smaller subsystem, is maximally entangled with the early Hawking radiation, what that means is that any subsystem of A prime is also maximally entangled with the early Hawking radiation. That's pretty obvious. And so in particular, I can take any quantum here, evolve it back to the near horizon zone, and claim that it is maximally entangled with the early Hawking radiation. So here's poor Alice falling into the black hole. wanting to see the Minkowski vacuum, which requires considerable entanglement of that very same mode, which is actually hugging this Rindler horizon. So these are very highly entangled things across the Rindler horizon. Alice requires this guy to be entangled with the interior of the black hole. So this is the equivalence principle part. Yeah, so I said all of this. I'm sorry, we're considering a quantum of the late radiation, evolving it back to near the horizon. And now we're looking at Alice. She wants flat space. And so she wants to see, so if I'm in the zone, I'm going to call this mode B. Okay, this is some Hawking particle that's currently on its way out while Alice is flying through the near horizon zone, about to cross the horizon. She needs this guy to be entangled with C, some inside mode, the guy on the other side of the Rindler horizon, in order for this to be the Minkowski vacuum. That's what the vacuum is. Okay, any departure, in particular, if we make this a product state or any order 1 departure from this entanglement, will mean that there's some energy density here that's basically that's set by the distance scale. And there are modes at different distances from the horizon that Alice encounters on her way in. So there's basically a lot of different entanglements that need to be there for her to see flat space. Okay, and so that's a contradiction. Right? We've already established that B is maximally entangled with some subsystem of the early Hawking radiation. It's maximally entangled with the early Hawking radiation. It cannot also be entangled with anything inside the black hole, not even a little bit. And a little bit wouldn't be enough anyway. Okay, so that's the problem. Okay, you can think of this as simply starting at the other end from where Hawking started. Okay, Hawking started by saying, I have the Minkowski vacuum here. I have the Minkowski vacuum here for Alice who falls in. And now I'm going to ask what happens at late times as a consequence. You start with the equivalence principle. You find a loss of unitarity. You find that you lose information. What these guys did is simply run the whole thing backwards. You assume no loss of unitarity. You assume the information comes out. And you run it back to the horizon. And you ask, can you have the equivalence principle for Alice jumping in? And the answer is no. And so if Hawking's calculation is wrong, it's wrong in a much more spectacular way than we anticipated. Right? The very assumption of this would seem to suggest that the very assumption of the equivalence principle holding at the horizon is wrong. That the horizon, if you want information to come out, the horizon must be a special place. Right? There's clearly something special going on here, even if we're just appealing to these S waves that make it out straight to large distances. The probability of encountering some particle here should be suppressed, should be exponentially suppressed by the equivalence principle, which should basically be impossible. And it's only area suppressed for S waves if you're flying through the zone. If you're small and the S waves are big, if you're small compared to the Schwarzschild radius, there is some suppression. You're not necessarily going to see anything. But the probability of seeing something is much larger than it's allowed to be. Okay. And in fact, the argument, and this is probably quite important, and I don't think it's been looked at enough. But there's a very beautiful argument that it's not just the S waves that are broken, where we're not getting the Minkowski vacuum. The vacuum is broken not just for the S waves that are coming out, it's also broken for the high L modes. And the argument goes as follows. It's quite nice. Apparently, you can mine a black hole. This is something that's been studied for other reasons already decades ago. And basically, the idea is the following. Okay, so here's the black hole. And sometimes it's emitting these S waves, which have almost no angular momentum barrier. They mostly get out to infinity. There's some order 1 probability for reflection, but it's not very close to 1. But then there are these higher L modes, which basically have some angular momentum, And they usually don't make it out, especially if L is large. So the black hole, again, right here it emits essentially thermally, so these modes are all, they're being produced, but they keep, they keep falling back in, and then they're here really high L ones. They don't get very far out at all, right? So there's some sort of, the lower the L, the further out they get before they fall back in. And for L equals 1, they almost get to the boundary of the zone to R equals 3m. And then for L equals 0, they usually get out all the way. So the question is, what about these high L modes, right? If I can show that they're all broken, that they're all maximally entangled already with the early Hawking radiation, so they can't be entangled with their friends here on the other side of the horizon, then not only do I have a pretty annoying violation of the equivalence principle, I have total death here, right? If I'm trying to fall in, because now every mode is broken. You can think of this as a bunch of Planckian wave packets sitting at the horizon, and then a bunch of slightly longer wavelength wave packets sitting near the horizon. If I can show that each one of these guys is already entangled with the early Hawking radiation, it cannot be entangled with the thing it has to be entangled with for free fall, for harmless free fall. And then I have essentially a divergent energy density, or one that's set by whatever my cutoff here is, perhaps Planckian. At the horizon, I would presumably have some huge back reaction. I mean, this is an argument by contradiction. It tells us what I can't have. It doesn't tell us what firewalls are, but it suggests that firewalls are extremely violent. You don't just have a conflict with the equivalence principle. You would actually die trying to fall into a black hole. The interior, in some sense, is not even there. So what's the argument for why these guys are entangled with the early Hawking radiation? The argument is that you can lower a box from far away into the near horizon zone, open it, shut it, and drag the box back out. And what this does is it helps these guys. So basically, the box is empty to start with. Near the horizon, it gets filled with thermal radiation. Because again, the box is an UNRU observer. It's an accelerated observer. It sees thermal radiation very hot near the horizon. The reason it seems so much hotter than at infinity is because it does see all these high L modes that don't make it over the barrier. So you shut them in the box and you drag them out. When you drag them out over the angular momentum barrier, now you have them. And the key point is, when you do this, the mass of the black hole goes down. It goes down basically by the mass of one Hawking quantum times the number of quanta that you grabbed. Okay? And so the entropy or information content of the black hole decreases when you mine the black hole. The mass goes down, the area goes down as a consequence. You've decreased the information content of the black hole. If you believe in unitarity, which is the assumption here, that means that the box of quanta that you grab must contain that information. You have to hold on to that if in the end you want to put it all together and actually recover the information. Right. And so the same logic applies to that box of quanta that you grabbed. In other words, to all these high L modes that are constantly being spewed out and falling back into the black hole, the same logic applies as applied to this S-wave quantum that just interpolated directly between infinity and the horizon. It must contain information. Therefore, it takes part in this whole argument that tells us that it's maximally entangled because it's part of a smaller subsystem. The black hole is less than half of the subsystem. It's maximally entangled. The content of the box is maximally entangled with the early Hawking radiation. Therefore, it cannot be maximally entangled with anything inside the black hole, or at all entangled with anything inside the black hole. Okay, and so, again, I want to stress that even at the level of just the S waves, this is a violent contradiction with the equivalence principle. You're not supposed to have such a large probability for seeing particles near the horizon. It's supposed to look like flat space. What this extra argument is just telling us is that it's personally a catastrophe for you and that there's no interior of the horizon. You would think that if your black hole is 1 billion light years across, that after you cross the horizon, you still have 1 billion years to live. But no, there's something bad happens right there.
Can I ask a question?
Yeah.
So, because A is outside the horizon and C is inside the horizon, what is a contradict that B?
Thank you. You've just, perfect. And I realize I'm running out of time, so I better hurry up. But this is precisely my point. I will. the question is precisely what I have on this slide. Why not use complementarity? So I want to explain why complementarity doesn't work. With some apologies to the people here where it's strings, where I claimed that it did work and showed exactly the same slide. So just a reminder, here's how complementarity helps with the Xeroxing paradox. We have this quantum Xeroxing, the star inside a black hole. Here's another copy of the information outside. Nobody can see both. Fine. Here we have the near-horizon modes entangled with something inside the black hole for the infalling observer. We have them entangled because of unitarity with the early Hawking radiation, according to the outside observer who wants unitarity. They can't talk to each other. Let's all be happy and go home. Same story, right? It just has to work the same way. Surely, this is going to pass all the same, Preskel-Hayden type tests where you do some actual, you try to see if you can somehow beat this by doing some experiments, and surely there's going to be a conspiracy again. But no, this time it doesn't work. And the basic reason for this, the basic reason why complementarity is not enough and why this argument is more powerful is that at least I am not aware of any obstruction to measuring the near horizon field. Remember, we're talking about modes which are in the zone, the region about, from the horizon to about 1 Schwarzschild radius away from the horizon. That includes a very large part of space-time where you can still turn around with less than Planckian acceleration. You can enter the zone, measure a bunch of these modes, and then turn around and go back out without anything terrible happening. And in that case, you're Bob. Okay, you're out at infinity, and you can verify unitarity. And so whatever you have measured for these modes before you fired your rockets and flew back out of the zone, even if you did decide to not fire the rockets, that fixes the quantum state. I can't give Alice, who falls in, a different quantum state from Bob, who stays outside, as far as these modes are concerned, because Alice didn't have to fall in. Right? We're not dealing with something where it's too late, where Alice is already inside the black hole, or at least at the stretched horizon, so that we would need super Planckian accelerations, and we don't understand the physics that wouldn't be necessary for Alice to get back out. No, we're dealing with a situation where everything's under control, Alice can measure these modes, and then decide whether to fall in or not. And that fixes the quantum state for these modes. If we want unitarity, it fixes them to a maximally entangled state between B and A. And then she can't fall in, because she's going to get fried by a firewall. Is this clear? Now, this is not completely obvious. I was certainly hoping that it would turn out that there are obstructions to measuring these modes. She doesn't have that much time. She's crossing this zone in a finite time. You can't measure them all that well. It doesn't seem to matter. It doesn't seem like you have to measure them all that well, because you can measure as many of them as you like. By making the black hole large, it seems like you can get very good statistics. And again, if you have maximal entanglement, you cannot have any entanglement or correlation between B and C. So there's really not a lot of room to maneuver. Yeah?
Just a clarification. We said that we took B as a subset of the late Hawking radiation, and we evolved it back to the near horizon, but then also C is in the subset of the late Hawking radiation. Now there's a subset of the late Hawking radiation, which is the first you're saying?
In this argument, well, to be completely, there's the mining argument, but let's leave that aside. So let's consider B to be an S-wave quantum that's making its way out from the horizon right now. So that tells me that it's maximally entangled with A, and therefore it cannot be at all entangled with C. At that point, it doesn't matter whether I consider C to be part of the late Hawking radiation in some perhaps complementarity sense. They're really the same thing, right? It doesn't matter. It doesn't matter what C is part of. What I need to fall in is I need something there that's entangled with B. And if B is already maximally entangled with something else, then I can stand on my head about C. It's not going to be maximally entangled or at all entangled with B. It really doesn't matter what I consider C to be part of. It's like this. So you knock your head against a brick wall. It's a terribly strong argument. So this does not work. So yeah, I already went through all of this. Sorry for not changing the slides. But I've already said that as far as I know, there's no obstruction to Alice, in fact, measuring the state of B, checking that B is. Now, there's actually one interesting obstruction that was recently pointed out by Harlow and Hayden, which is not an obstruction to measuring B, but it is an obstruction to checking whether B is actually entangled with A. And the reason why that's hard is that A is expected to be a very highly scrambled state. So, in other words, you have Hawking quanta which, you know, naturally, well, there's this part of the radiation, that part of the radiation in space, or there's this quantum coming out, there's that quantum. If you grab onto any of these quanta, or even if you measure the state in a basis that's sort of a product state basis over all of these quanta, you usually don't learn very much. It's the wrong basis. If you start with some initial quantum state, you wait for the whole black hole to evaporate, and you look at the final state of the Hawking particles, it'll be some terribly complicated linear combination of the product states of Hawking quanta, which makes it, you know, you really have to look at the whole thing and then use a very powerful quantum computer to extract the information for you. And what these guys showed is that this takes an exponentially long time to do under fairly weak assumptions. In other words, if I want to unscramble the early Hawking radiation so that I could actually check if this radiation in the zone is in the correct entangled state with it, I wouldn't, you know, it would take me an exponentially long time to do so, by which time the black hole has already completely evaporated and I have nothing to jump into. This is a nice attempt, and I think it fits into my final slide, which is to not give up. I find it absolutely obnoxious to think that the equivalence principle would be violated at a black hole horizon. But I really don't know what to do about it, and I'm not optimistic, even about this argument. And the reason is basically linearity. In fact, my suspicion is that if you want to get rid of firewalls, you have to violate quantum mechanical linearity for the infalling observer. For example, I can certainly find a complete basis of states in which the outgoing Hawking radiation is in fact in a product state of all the quanta. I have to make the black hole in an extremely special, fine-tuned way for each one of these states to actually, to actually be realized. But by linearity, they exist. And by linearity, they span the whole Hilbert space. And in each of these states, I have no problem decoding anything. It's completely manifest that the near horizon zone is in a pure state, so it can't be entangled with anything inside the black hole. And I must have a firewall. Now, you can start thinking about whether it's possible to have a firewall in every basis state, but not in typical linear combinations. And unless you have some positivity property of what characterizes a firewall, it may be possible to arrange that, but I'm very skeptical. And there are other objections that one could raise against this argument. So that's kind of where I want to leave off. I think that there are two ways that we can progress here. One is what I would like to do, which is to preserve the equivalence principle and ask what will it take, and sort of really push that. I mean, maybe at the end you'll get to something that's just so unacceptable, like to some people violating quantum mechanics seems. It seems like modifying quantum mechanics is already pretty unacceptable, but perhaps that's the way to go. The other direction, which in my mind is really the same direction, is to try to make sense of firewalls. What are they? How do they form dynamically? Do they really just form at the page time when half the black hole is evaporated, or do they already form earlier and we just don't have such good arguments for them earlier? I suspect that if there are firewalls, they form pretty soon. But try to work with the firewalls and run them into the ground, because I don't like firewalls. But maybe by assuming they're there and seeing what sort of bizarreness they lead to, one can discover exactly how to argue against them. But that's why this is really, I think, the greatest opportunity that's come along in the field of quantum gravity probably for 40 years. I mean, we had Hawking's result that information is lost. 20 years later, people started forming a consensus that we'd sorted this out, and it's not lost and everything is okay. And now I think we're back to square one, but sort of on a higher level. I think we have much more evidence for unitarity than before from ADS-CFT. We can run it back and we can see that you cannot fall into a black hole. It's just an amazingly strong paradox. It's absolutely beautiful. It pits the two very basic principles of the two things that we're trying to unify against each other, equivalence principle and unitarity. You guys are incredibly lucky. Okay, I mean, this is the time. This is, when you have such a sharp paradox, it really gives you leverage. It really, perhaps you can just follow it to the bitter end and see what has to give. And whatever has to give is going to be big. So that's it. Thanks. Krishna, yeah.
So I'm going to attempt to ask you a question that grows out of a lunchtime conversation that I had with several other people in your audience. So we could be, according to classical general relativity, we could be falling through a horizon of a very large black hole right now, or we could have fallen through such a horizon yesterday. So we could be Alice, gone through. Now, that very, very large black hole has not had time, anywhere near half of its Hawking evaporation time yet, so it's not old enough for the considerations you described to apply. But I guess my question is if suppose firewalls are the answer for the old black holes that you described, is there some precursor of them? So this big black hole that we just fell through, it doesn't yet have a fully developed firewall because it's not it's not yet old enough. But nevertheless, as we went through that horizon, is there some precursor of the firewall that if we were smart enough, we could have detected?
To answer that question, we would have to have a much better understanding of firewalls. And there are different models that at least have floated around in my mind, and I think people have played with. One possibility is that the firewall forms right after the scrambling time, so when the black hole settles down into its no-hair form. That's essentially the earliest time it could form. It forms a lot earlier than that. We get violations of causality, because we might not even, by causality, be able to know that we're crossing an event horizon. And let me just finish that. So in that case, if you fall in before the scrambling time, you're not surprised to see a little bit of mess because the black hole's still settling down. And then if you fell in after, you might already see a full-fledged firewall. The AMPS argument doesn't apply as directly to this case, but if you believe in linearity, for example, it's fairly plausible that that's actually the case. Because again, you could consider a basis of states in each of which the Hawking radiation that comes out is actually in a product state for each Hawking quantum from the beginning. That's a complete basis. And in each of these basis states, you certainly have a firewall. So then you'd have to argue that in typical states you don't. It's possible. So we don't know. The other option is that the firewall in some way builds up gradually over the page time. And there are models that you can write down for that as well. And it's probably linear. And then what would happen if you fall into a black hole at early times is you'll probably see a few flashes in the sky. And if you jump in somewhat later, you'll see more flashes in the sky. And if you jump in later, you get pretty hot while you fly in. And but to really, we don't know what happens in the first page time, even if we believe that there are firewalls, and this argument goes through unmodified for old black holes.
I want to tie it to the previous talk by Giudice. So if you see a few flashes on the sky, and you were clever experimentalists, and you see those flashes, that seems to be a profound violation of sort of the principles of effective field theory.
Absolutely, yes.
And so how do you define when effective field theory is okay and when it's not?
I have no idea, and that's why I hate firewalls. I really hate them. It's just that, you know, it's just not, this is what's so great here. You just have no room to maneuver. I don't know what to do. I hate them, but I don't want to give up unitarity. What to do?
You know, there's going to be a discussion later on at 5 in the theory conference room with Raphael. So if you want to continue the discussion, that's the right place to take it.
I guess that's pretty soon.
We have the coffee break now, or do you want to have a quick question, Knowledge? Okay, please. Last one.
Yes, I'm sorry. In the framework of ADS-CFT, where there was a resolution of the information paradox and the unitarity was explained somehow, okay? What would be the analog on the side of the conformal field theory of the firewall?
Well, notice that what's being proposed here is no modification whatsoever to the story that we were always going to give Bob. From the outside viewpoint, there was always something special at the horizon. If you probe that region, it's very hot. It's like there's a membrane there. Information comes from there. And that's still the story for the outside viewpoint. It's only if you fall in that it seems like you have this very violent behavior that we thought we didn't need to have there. Now, my personal viewpoint is that ADS-CFT cannot possibly teach us anything about the infalling observer if we don't understand the bulk equations locally to start with. Because the way that we reconstruct the bulk from ADS-CFT is, well, either we're dealing with observables that are essentially defined far out near the boundary where the correspondence is very direct, something like a scattering matrix which translates into CFT correlation functions, so local operators in the CFT. Or we need to use the bulk equations of motion to reconstruct, to basically evolve inward from the boundary and reconstruct the bulk. And of course, that'll only be possible at some semi-classical level because, as was pointed out, you know, from that viewpoint, there's never really definitely a black hole there. There's always some small probability that maybe it's not there. But in any case, even at that level, you need to know the bulk equations of motion in some intrinsic way. To get this approximate geometry back, you need to know locally how to do the bulk theory. And that's what we're debating. If there are firewalls, then there's nothing to evolve from anymore once you've crossed the horizon. That's it. There's some singularity there. Now, people are thinking about whether there are clever ways that one could look for signatures of that using ADS-CFT. I know Eva Silverstein is thinking about that. Maybe Eliezer is thinking about that. They've both been pioneers in trying to understand how you get information about the interior of a black hole in the CFT. And you know, perhaps like, personally, I'm skeptical. I've always been skeptical that you can really learn anything about the interior that goes beyond semi-classical gravity. But I may be wrong. And maybe there are ways of maybe Eliezer wants to comment on that. But maybe there are ways of testing for the existence of firewalls in the CFT.
Well, I think that we should break for the coffee break first. And let's thank Raphael for our magnificent lecture.
Thank you.